To dig a little deeper into phase transitions, I want to examine some of the thermodynamics that's involved in that. And to do this, I'm going to use a simple heating curve to illustrate some of the points I want to make. Now, this heating curve is something that you've probably seen different versions of. I'm going to also further specify that we're going to heat this substance up at constant pressure, and that pressure could be 1 atmosphere. I mean, let's just make it simple. All right, so we'll make a graph here. And the vertical axis is going to be temperature in this case. Normally we have temperature on the horizontal axis for some reason, but now I'm going to make it the vertical axis. And along the horizontal axis, I'm going to draw the heat at constant pressure. Now I could have also labeled that the enthalpy because they are equivalent, but I'll leave it at that for now. Now, as we heat something up at constant pressure, I mean, let's say down here at very low amount of heat and very low temperature, that some substance is going to increase fairly linearly in temperature and in heat. And in fact, this slope of this curve would be related to the heat capacity of the substance. So I'll say it'll be 1 over Cp. Now, down in this region, we're going to say that we have a solid. So this would be the heat capacity that is relevant for the solid. Now we're going to reach a certain point here where all of a sudden we're not going to be increasing the temperature anymore. So I'll draw this down here, and I will draw across here that this temperature that we've reached is basically the temperature of fusion. And at that temperature, we're going to find that the temperature doesn't change while we're adding heat. In fact, what's happening at this point is we are converting solid substance into liquid substance. Now, once we get over and have converted everything to a liquid, we'll again start climbing, this time with a different slope. The different slope now is the 1 over the heat capacity of the liquid, because this is a region in which we have a liquid present, but no solid. All right, now I should also probably label this change. This is a heat variance, it's an enthalpy variance. It is basically the enthalpy of fusion for this substance. That's how much enthalpy it takes at the temperature of fusion to convert, let's say 1 mole of this stuff, then it would be a molar enthalpy, to convert that substance into a liquid. Now, once again, we're going to get to a point up here where we're no longer going to change temperature, so I'll draw a line across here from that. And this line will represent and will help label for us the vaporization temperature. And of course, at this point now, we will have another flat area on this curve, at the end of which we will again begin to climb. And this climb now will be associated, the slope being 1 over the heat capacity of the vapor. All right, so we've gone from solid to liquid and now to vapor. And I didn't make my horizontal axis big enough, apparently. So here is our vapor. This change here represents delta vaporization of enthalpy. All right, so what we see going on here is that we hit these periodic places where the temperature doesn't change, but we're still adding heat. In essence, what's happening is all of the heat at these places is being used to convert, in this case, liquid to vapor. So it is taking a substance that is in the liquid phase, and the heat is not going to raise the temperature, it is going into converting liquid molecules to vapor molecules. All right, so as we're going through this, during the phase transition itself, we're not seeing a change in the temperature. And we've already indicated that this was indicative of some kind of equilibrium that's going on in the process, even though we have a non-zero delta H, and let's focus on vaporization. So I have a non-zero delta H. I actually know that the delta vaporization of entropy, and both of these are going to be greater than 0, because the delta vaporization of entropy is simply the delta vaporization of enthalpy over that temperature. So Since both of these things are greater than 0, I can define and I can define them. I can also define the Gibbs energy change, and that Gibbs energy change during the course of this phase transition, it turns out, will be equal to 0. So in other words, this is the magic temperature at which delta vap of enthalpy minus T delta S vap of entropy is equal to 0. So that defines for us the value of vaporization. Okay, so under 1 atmosphere, I should be careful to add. All right, so what is all of this telling us? We've got an equilibrium that's going on here, and how can we think about that equilibrium? Well, I want to think about it in terms of a simple molecular picture. So I'm going to draw, this is a poor man's drawing of a liquid, and all of these are molecules in the liquid, and they're bouncing around and they're bumping into each other. There are also going to be, however, some of the molecules up here near the surface that manage to escape. And when they escape, that is the process of vaporization. They come up here into the gas phase, and we'll have a few other molecules in the gas phase. But some of those gas phase molecules are also going to be coming down, hitting the liquid, and rejoining the liquid. So we have movement going in all directions. We all, gas phase molecules moving in various directions here as well. So it's a dynamic process that's going on. This is what I'm trying to indicate. So the equilibrium that's involved doesn't mean that all of the molecules that are liquid stay in the liquid and all the molecules in the gas phase stay in the gas phase. They're being actively exchanged all along. And that's what describes a dynamic equilibrium. And if you haven't studied much about dynamic equilibria, we are surrounded by them all the time. And in fact, if you're a chemist, you know about dynamic equilibrium because chemical equilibrium is a dynamic equilibrium. It's basically characterized by a couple of key indicators. One, it's a closed system. That is to say, it is not exchanging matter with any other part of the universe. In general, it has mobile subunits. In this case, our subunits are molecules. And a third piece of this is that it involves a process that is reversible. And in this case, the reversibility is some molecules go into the gas phase and other molecules come down from the gas phase and join the liquid phase. And what happens is we reach an equilibrium when the rate of molecules going up into the gas phase is equal to the rate of molecules coming down into the liquid phase. So that's what creates this dynamic equilibrium that really is what phase transition represents. Now, one thing I want to clarify here is what sets that equilibrium? In this particular case, as long as we're at constant pressure, and I want to maintain that condition for us for now, the condition of this equilibrium is really determined by the temperature. So temperature sets the position of phase equilibrium. What does that mean exactly? Well, let's suppose that I'm at an equilibrium here with my liquid and my gas phase up in this upper picture here, and I increase the temperature. What's going to happen? Well, intuitively we know that more of the liquid's going to go into the gas phase, but why is that? Well, when I increase the temperature, I'm making everything move faster. And so that means that some of the molecules that are here on the top of the liquid are going to have a little bit more kinetic energy and therefore a little bit greater probability to leave the liquid phase and enter the gas phase. Also, the molecules up in the gas phase are going to be moving faster also. So when they come down like this one and happen to hit the liquid phase, if they're moving too fast, they may just bounce off that liquid surface. So there's a lower probability for them to be reabsorbed by the liquid. The same or the opposite thing happens when I lower the temperature. When I lower the temperature, now things are moving more slowly. So that makes it harder for liquid molecules to escape the liquid and easier for gas phase molecules to enter the liquid if they should collide with its surface. So in this sense, temperature is really tuning this system and changing the position of this equilibrium so that it favors either vaporization or condensation. Now, I also want to note that we have talked about both enthalpy and entropy as functions of temperature, and we've even shown graphs of them, how they change as functions of temperature. Well, remember that the delta H involved with vaporization and the delta S involved with vaporization involve these functions of temperature, so they also are functions of temperature. Now, that may surprise you, but what it basically means is that they are not constants, although we treat them often as constants in our calculations. As T increases, in fact, these two quantities also change. And in fact, what I will tell you is that the delta H of vaporization actually decreases. In other words, it becomes easier to take molecules from the liquid phase into the gas phase. I think that makes a little bit of sense. If I increase the temperature, they're moving faster, so it's not going to take as much energy to span this gap to get those molecules to leave the liquid phase and enter the gas phase. All right, the bottom line for all of this are some really key points. Okay, I've indicated that the vaporization of the Gibbs energy at this phase transition is 0, but it is also true for the molar Gibbs energy, and that's going to be something that we'll care about even more very shortly. But we can write this, if you will, as the molar Gibbs energy of the vapor minus the molar Gibbs energy of the liquid. So in other words, if this is equal to 0 at a phase transition, that's telling us that at that phase transition, the molar Gibbs energy at Tvap is equal to the molar Gibbs energy of the liquid at that same temperature. And this is an equation that more or less defines for us what this equilibrium process is like for a phase transition. Now, I will note once again, we will get very similar kinds of expressions if we talk about the phase transition that goes from solid to liquid or from solid to vapor. So this is not exclusive to the vaporization process, but we're using vaporization in particular in this lesson because that's the key phase transition that I want to highlight at this point in the course.